This demo shows the use case scenario of privacy-preserving anomaly detection, applied on electric vehicle charging transaction logs. During the charging process of electric vehicles, the Open Charge Point Protocol, or OCPP, is utilized by the charging stations, in order to transmit measurements that indicate the energy consumption during the charging process. These measurements are used by the charging station operator, for billing the charging session. However, the charging process is vulnerable to cyber attacks, since the electricity measurements are transmitted unencrypted and unsigned. There are also privacy concerns, since the electric vehicle charging data is considered private information, risking potential eavesdropping and profiling of energy usage by malicious actors. In this demo, a cyber attacker performs an energy theft attack by altering the OCPP meter values messages transmitted by the charging station to the charging station operator. The cyber attacker modifies the watt-hours values in the meter values messages transmitted during a charging transaction, aiming to reduce the total billing amount of the charging transaction. In order for the tampering to be detected, the electric vehicle charging curves should be analyzed for potential deviations. To deal with the potential tampering of EV charging data, a privacy-preserving anomaly detection solution is applied by ELECTRON. In more detail, PPC, which is the charging station operator, submits periodically EV charging transaction logs to IBM for analysis. After encrypting the logs, they undergo analysis by the fully homomorphic encryption, or FHE, anomaly detection module of IBM for potential tampering, utilizing the autoregressive integrated moving average method. If an anomaly is detected, the FHE anomaly detection module generates an encrypted security alert, which is delivered to the ELECTRON security information and event management system, which in turn decrypts the alert and visualizes it on the dashboard, thus notifying the security administrator for the potential anomaly. The scenario is initialized by setting up the digital certificates necessary for the FHE anomaly detection module to verify and authenticate the digital signatures used to ensure the integrity of the EV charging logs. The certificates have been sent to the IBM team via email. The certificates are in binary format, however, we can open a certificate and see how it looks like. Now that the certificates are configured, the FHE anomaly detection component is ready to receive new EV charging logs. In this screen, you can see the command line terminal of the charging station management system. It is a web-based software platform that handles and authorizes the EV charging transactions. Moreover, this system receives the electricity measurements during each transaction. At the end of each charging session, the charging station management system will upload the measurements log file to the IBM Cloud Object Storage, in order to be received by the log aggregator and the FHE. On the right terminal, we are starting the IBM Cloud Object Storage monitor process, which automatically uploads new log files to the cloud. On the left terminal, we will copy a log file of a completed transaction to the monitored folder. Since this is the first log we are submitting, this is considered normal by default, and will be used by FHE to get the baseline, and train the ARIMA model. On the IBM side, the IBM Cloud Object Storage Receiver downloads the new log file, and subsequently deletes it from the cloud storage. A subcomponent of the FHE module passes the JSON file, and converts it to CSV format. Here we see the log aggregator component, which takes the CSV file and aggregates the data, to create an encrypted log, utilizing the FHE method. The aggregator encrypted the log and signed it with the digital signature, shown at the beginning of the demo. Next, the FHE anomaly detection module sees that a new encrypted log has been saved, and it starts to apply analysis on the encrypted log. Because this is the first log, it is considered non-anomalous by default. It is used to train the ARIMA model and check if future logs contain any anomaly. Returning back to the charging station management system, Now we are going to send a charging transaction log, which contains meter values that have been tampered with. On the IBM side, we see that the receiver module has received the log file, and then has deleted it from the cloud storage. As usual, the JSON log file is converted into CSV format, and the aggregator aggregates, encrypts, signs, and saves the log file. Next, the FHE anomaly detection module gets the encrypted log and authenticates successfully the log's digital signature, indicating the valid integrity of the log file. Once the signature verification is successful, the analyzer proceeds with checking the log file for potential anomalies. Now, this is the part where all of the FHE computations happen. The analyzer receives and analyzes an encrypted log that it cannot actually see. However, due to the FHE encryption, the analyzer is able to apply computations on the encrypted data, without any need to decrypt this data. So, the ARIMA model is trained on encrypted data, and then is used to detect anomalies on subsequent encrypted data. The analyzer has now finished with the computations, and it produced an encrypted report, which specifies whether any anomalies have been detected. This encrypted report is saved and signed, and will be sent to the alert decryptor of the ELECTRON security information and event management system. It should be noted that, for the demo purposes, we used a less secure encryption, in order to make the computations run faster. We could also run on fully secure encryption, but it would have taken several minutes to complete the computations and produce the detection results. Finally, moving to the ELECTRON security information and event management system, we are logging to the dashboard of the tool, in order to see the contents of the security report generated by the FHE detector. All the security reports are sent to the SIEM agent, which validates and normalizes all the information. In this page, we can see all the normalized events that have been received from the FHE detector module. By opening a security event, we can see various useful information. For example, we see the raw log corresponding to the security event. The raw log is constructed by the FHE module, and is the main source for constructing the normalized event. We can see the date, when the anomaly was detected. We also see the type and category of the event. We also have the data source, which indicates the ELECTRON component that generated the security event. We also have information related to the network, like the IP address. In this case, based on the OCPP logs, we provide as victim the IP address of the EV charging station. This aims to help the security administrator to identify and narrow down the compromised communication channel. Finally, we have information specific to the sensor that is placed in the user data fields. In those fields, we have the ID tag, which is the RFID tag used as identification by the EV user. The RFID tag is used by the EV user in order to get authorization for a charging transaction, and to be billed accordingly. This is a very sensitive information, and can be used to reveal the identity of an EV user, and associate them with private EV charging data. Then, we have the transaction ID, which is the unique ID of the transaction within the charging station management system. We also have the expected value of the state of charge, as well as the actual value that was observed by the FHE analyzer. Moreover, we also have the state of charge range, which indicates the particular part of the charging curve where the anomaly was detected.